So first, I want to thank for the opportunity to give a talk at this seminar. So this is the title of my talk, The Spectral Geometry in a Rotating Frame, Properties of the Ground State. And this is a joint work with Pavel Exner, who is working in Prague in Institute of Nuclear Physics. So next slide, please. During this talk, we will consider the following self-adjoint differential operator. So this is this is the Hamiltonian. This operator is given in the two-dimensional space, more precisely in the bounded domain in the two-dimensional space R2. The omega is the domain where this operator is defined. The first component is the Laplace operator, minus delta is the Laplacian, usual Laplacian. Then we have the perturbation of this Laplace operator. The x and the y are the partial derivatives with respect to x and y are the variables in R2. Next, we have here x0 and y0. This is the fixed point, but it can be any point in the R2. Then we have the imaginary unit I and the constant omega. The constant omega is supposed to be positive constant. And we will look on this operator, and then we will speak about the spectral properties of this operator. So, next slide, please. This operator comes from the physics, and it describes the quantum particle, which is confined in a domain omega, and which is rotated around the fixed point x0, y0 with the velocity omega. So this x0 and y0 and omega appeared now in the Hamiltonian of this operator. And this operator also gives some information, appears in connection with the properties of ultra-cold gases. So it has some physical motivation. And there are two papers which are written here, Rongaglia, Rizzi, and Dalibard, and first paper, and Lieb-Zeiringel. So there are at least two papers where this operator appears with, in connection with the physical properties of the ultra-cold gases. Therefore, it has some physical motivation. Next slide, please. First of all, we will speak about the self-adjointness of operator H omega. And after that, we are able to speak about the spectral properties of this operator. How to construct its self-adjoint extension. First, we will look on the functions from C0 infinity omega. So this means that there are functions which are infinitely differentiable functions with compact support in omega. And then we calculate the quadratic form, which is the left-hand side of this equation, of H omega x0, y0 at u. When you calculate it, then you get this expression on the right-hand side. So first part is the magnetic operator, magnetic Laplace operator, this I nabla u plus a hat u, where a hat is the magnetic potential, which is given down below, minus y plus y0, x minus x0. Then we have the electric potential, minus y squared over 4, and this integral. So this is our expression of the quadratic form. Now, we use the fact that omega is a bounded domain. So this means that the second component of the right-hand side of this equation is bounded, because x0 and y0 are fixed points and x and y are bounded. And of course, u is from L2. Therefore, the second negative part of the right-hand side is bounded, and the first one is non-negative. Therefore, in this situation, since we have here bounded from below quadratic form, and also, of course, one can check that this Hamiltonian is symmetric, this operator is symmetric, then from the theory of self-adjoint theory of operators, one can guarantee the existence of the self-adjoint extension of H omega x0, y0. The extension of the extension from the case when u belongs to C0 infinity. And the extension is constructed using the so-called Friedrichs method. And this operator, resulting operator, is called the Friedrichs extension. And is written as the following, as the last equation, h omega hat x0, y0. Also, one can prove that the domain is the intersection of these two Sobolev spaces, h2 and h10. This means that these are the functions from the Sobolev space h2, and with the trace equal to 0. So the values, the trace of function u at the boundary equal to 0. But and here you have again the Laplace, the Laplacian, magnetic Laplacian part and the electric part. Next slide, please. Since the magnetic potential here, as we remember, is the form y minus y0, x minus x0, we want to have the more beautiful, more nicer formulation of the presentation of the magnetic potential as written in this file, in this slide, without x0, y0. And the idea is now to use the gauge transformation, which is given as before us in the first line, from uxy go to uxy, multiply by this e of order minus I omega xy0 minus yx0 over 2. And using this gauge transformation, you are able to pass from the operator h omega hat x0, y0 to another operator, tilde, which is written below, which is, and these but operators are unitarily equivalent. And why we need this? We will now work with the nicer operators, unitarily equivalent nicer operator h omega tilde. And it's very well known that two unitarily equivalent operators have the same similar spectral properties. So what we prove for these operators, it's also true for the original operators. Therefore, we do this step. And now we see now already these operators, h omega tilde. And the first part is the magnetic Laplace part, but already with the magnetic potential minus yx, this potential. And the electric part is the same. The next slide, please. So first of all, since this part with the electric potential is bounded and the magnetic Laplace operator has poorly discrete spectrum on the bounded domain, from the minimax principle follows that this operator h omega tilde has also poorly discrete spectrum. And during our talk, we will consider mainly the ground state eigenvalue λ1 omega x0 y0 of this operator. So this λ1 omega is the principal or first eigenvalue of our operator. Next, please. We will speak about three questions. We will discuss three questions about these operators, about this first eigenvalue. First question is the so-called optimization of λ1 omega x0 y0 with respect to the position of the rotation center. So this means that the rotation center in this in our formulation is x0 y0, and now this first question means where to put x0 y0 to have the minimum or maximum of λ1 omega. Because x0 y0 is the any point from R2, therefore this question is natural question. The next question is already you fix x0 y0 and now look as this function as the function of the velocity omega. And the third question which we do, so we have the domain omega and then we fix its volume, and then we look on the disk with the center at 0 and the same volume as omega. And then you will look on this operator already defined on disk with rotational center x0 at origin, and look on the ground state eigenvalue, which is λ1b omega 0, 0. Then we look at the difference between our operator defined on general domain omega and this difference with the eigenvalue defined operator defined on the disk with the same area. and estimate this expression, the last expression, in terms of the geometry omega. So these are three questions which we will speak about. First, we will start from the first question. So this is the first question. For any x0, y0, we construct the function lambda 1 omega x0, y0. And the omega domain and the small omega velocity are fixed, and only change is the variable now is this x0, y0. And the questions to prove the existence of extremal points, and the question where to put to get the extremum. So first theorem, we prove that lambda 1 omega as a map from R2 to R has no minimum, but it has a unique maximum. First, we'll prove that this is no minimum and it has a unique maximum. And how to prove this result? I will give a small sketch of the proof of this result. First, next slide, please. This first theorem, the next theorem which we prove is so-called is the part of the sketch of the proof of the first result. We first prove that lambda 1 omega has no minimum, so it goes to minus infinity when the variable x0, y0 goes to infinity. And then we prove that if it has a maximum, then this maximum is unique. And the next slide, please. And also we combine with this with remark that if the variable x0, y0 goes to infinity, then the ground state eigenvalue goes to minus infinity. So what we have from these two theorem and remark? We prove that this mapping has no minimum. And if it has a maximum, then this maximum is unique. But the existence of the maximum is guaranteed with this remark because the lambda 1 omega goes to minus infinity at infinity. And so therefore it follows, since we also prove that this mapping is continuous, follows that the maximum exists. And then after that we prove that this maximum is unique. So the statement is that it has a unique maximum and has no minimum. Next, please. We give a sketch of the proof of the first theorem, of this theorem, that it has no minimum. So this is a sketch of the proof. So suppose that the x0, y0 is a possible extremum point, and we are going to prove that it should not be the point of minimum. We now employ the perturbation theory, methods of the perturbation theory, and construct the eigenfunctions, normalized eigenfunctions, u omega x0, y0, and v omega x0, y0, which corresponding to the ground state eigenvalue, such that these two expressions takes place. There appears one problem to construct that, because since we know that the ground state eigenvalue is simple, then its situation becomes more easier. And then you can say that u omega should be equal to v omega. And also the steps becomes more easier. But in our situation, we are not able to guarantee that the ground state eigenvalue is simple eigenvalue. And also we'll construct the example that this is not true. In general, it's not true. There are examples that shows that the ground state eigenvalue is not simple. Therefore, to apply the more standard method of perturbation theory becomes not possible, impossible in this case. But nevertheless, to guarantee the existence of such eigenfunctions existence of such eigenfunctions is guaranteed. So, for example, you can check this from this book, Raymond, Bound States of the Magnetic Schrödinger Operators. So next slide, please. And now the key point is to prove the following. Suppose that x0, y0 is the point of extremum. After that, we prove that these two equations, that these but integrals, should be equal to 0. So this is the key point of our proof. And once we have this equal to 0, after that we will prove that this point is point of maximum. So now we will prove these two equations. We do this by the contradiction, and we suppose that this is not true. So at least one of these but integrals does not equal to 0. And without loss of generality, suppose that first one is not 0. And so first one, suppose that it will be positive. The negative, it will be the same proof. So let this integral will be positive. And in this case, we choose the negative small enough number h, and then look at the lambda 1 omega at point x0 plus h and y0. So we now look on just x0 plus h and y0. And now, using the minimax principle, any ground state eigenvalue can be estimated via the infimum of the quadratic form of operator. Therefore, the ground state eigenvalue corresponding to x0 plus h y0 is no larger than the quadratic form applied at u omega x0 y0. And then we calculate this Hamiltonian as the quadratic form corresponding to the unperturbed Hamiltonian, and plus something. And this something in the blue written, which has the order h, only h has order 1, and the last part has the order 2. And since we suppose that this integral is positive and h is negative, then it follows that the second component is negative. And since the last component has the order 2, therefore it follows that this expression is less than what we have in the last line. And of course, this is the ground state eigenvalue corresponding to x0, y0. So here we prove that supposing that x0, y0 is the point of extremum, lambda 1 omega x0 plus h y0 is no larger than the unperturbed eigenvalue. So next, please. Now we are going to prove the opposite inequality. We supposed before that this integral is positive. Now, using the fact that, again the perturbation theory, one can prove that if you add some small enough t, sufficiently small t, then the second integral, given in the second line, should also be positive. Next, please. And now we choose already positive t, small enough. Now try to estimate already from above this ground state eigenvalue. And again, using the perturbation, the minimax principle, this ground state eigenvalue can be estimated from above via the quadratic form of unperturbed operator applied at u x0 plus t y0. Then we do again the calculations, give this line, and now and again having that this integral x minus x0 u omega square is positive and t is already again positive, then the second component should be negative, and it has the order 1, t has order 1 t, and the last one has order t square. Therefore, this we prove now that this line is less than the last line. Last line is the operator, the quadratic form of operator h omega tilde x0 plus t y0 applied at its ground state eigenfunction, and which is of course the ground state eigenfunction corresponding to x0 plus t y0. So we already proved the opposite inequality. So next, please. What we have here, we proved that for negative small enough h, we have this upper inequality, that the lambda 1 omega x0 y0 is larger than if you change this x0. And also we proved that if t is negative, then we have the opposite inequality. This ground state eigenvalue already less. So therefore it proved that x0 cannot be the stationary point, x0 y0 cannot be the stationary point of the ground state eigenfunction. Therefore, we will prove that, next please, we prove that these bad conditions are necessary condition for the fact that x0, y0 is the point of or maximum or minimum, is a point of extremum of the ground state eigenvalue. So they are written here. Now, having these two equations, we will prove easily that x0, y0 can be only the point of maximum. Next, please. Now we will have any h small enough number. Then we can look on the perturb eigenfunction, eigenvalue, lambda1 omega x0 plus h y0, use the minimax principle, estimate it via the Hamiltonian corresponding to this eigenvalue, but apply it at u omega x0 y0, then calculate it, get the unperturbed operator applied on its eigenfunction minus some positive number. So therefore, it's less than the ground state eigenvalue. So this means that ground state eigenvalue corresponding to x0, y0 is always larger. Therefore, it's point of maximum. So we prove that this operator has only one point of maximum and it has no point of minimum. And if x goes to x0, y0 goes to infinity, it goes to minus infinity. Next, please. So this is the first part of the question. Now the questions connecting with the position of x0, y0, where this eigenvalue attains its maximum. In general, it's very difficult to ask this question, but in some specific cases, at least if omega is a convex domain, you can say more information about the position of the extreme of the maximum. So we prove that if omega is a convex set, then this mapping reaches its maximum at a point which belongs to omega. Because in general, you are not able to say that it should be always belonging to omega. Next, please. Again, here I will give some idea of its proof. Here it's written two equations which already prove that they are necessary conditions that x0, y0 is a maximum. So they are written. And from here follows that x0 should belong to the projection of omega at the line x. And y0 must belong to the projection of omega at the line y, at the axis y. Why this is so? Because in other case, if x0, for example, x0 does not belong to the projection, then x minus x0 has the same sign, and then we have the integral. Therefore, it should be or negative or positive, but not zero. Therefore, we have this implication. Next, please. Also, now let's remember we using the original formulation of our operator and passing to the polar coordinates can rewrite our operator in the polar coordinates. So you see the first it should be minus, it's misprint, should be minus in front of Laplace. Minus delta d omega is the Laplace operator written in the polar coordinates. Next, we have def phi. Def phi is the partial derivative with respect to phi. And our phi, of course, are the polar coordinates. So you see here that if you rotate the system of the coordinates, then you have the same spectral properties. Therefore, we use this formulation to show that these spectral properties are invariant with respect to the rotation. Next, please. Now, supposing that x0, y0 does not belong to the domain omega, and using the important fact that omega is a convex set, you can always rotate the system of the coordinate in such a way that at least one from these equations, at least one from these formulas, x0 belongs to projection and y0 belongs to projection, will not be satisfied. But to do this, we use the fact that omega is a convex set. Therefore, if we rotate in this way such that at least one from these formulas do not satisfy, then we will have the contradiction with the fact that x0, y0 is a point of maximum, point of extremum. Therefore, we prove that for the convex sets, of course, always the maximal point belongs to the domain. It's located inside of the domain. Next, please. Now, if omega is small enough, then you can again say, you can also say about the position where inside of the domain you can put this point. For this, we give the following definition. In general definition, let sigma be a region in R2, and we have the line P in sigma. We denote by sigma P is the mirror image of sigma with respect to P. Sorry, P does not belong to sigma, mistake. We have the given region sigma and line P, and we denote by sigma P the mirror image of sigma with respect to P. Next, please. Then we have here the theorem, which presents, which gives more information about the localization of the point of extremum in the situation when the domain is convex. So suppose that omega is a convex set, and let P is the line which divides omega into two parts, omega 1 and omega 2. But in this way that the mirror image omega P of omega 1, omega 1 P is included in omega 2. So roughly speaking, omega is divided into two parts. One is smaller, one is larger. So the mirror image of the smaller is included in the larger. Then for small enough values of omega, you can say that the maximal point of maximum of this mapping, lambda 1 omega, attains in the larger part of omega. So the point of maximum where lambda 1 omega attains its maximum does not belong to omega 1. So it belongs to the larger part of the omega. Next, please. And again, I will give some idea of this proof. We will first consider the situation where the rotation is absent. This means that omega equal to 0. So in this case, we will have only the Laplace operator, the Dirichlet Laplace operator, and the eigenvalue will be the Laplace first eigenvalue. And the eigenfunction is denoted by ud, so minus delta omega d ud equal to lambda 1 d ud. Then we are going to prove that the integral, in this case, if x0, y0 belongs to smallest part, omega 1, then this integral is positive. Next, please. Then we are going to use the perturbation theory, standard perturbation theory. Here we can apply this perturbation theory because we know that the ground state eigenvalue corresponding to the Laplace operator on a bounded domain is simple. Therefore, by standard perturbation theory, the ground state eigenvalue, eigenfunction, if we perturb this operator, give the small perturbation of the Laplace operator, can be written as the perturbation of the ground state eigenfunction plus this part or large omega. Yes, this part. And after that, since we already will prove that this integral, first integral written in the first formula is positive, then using this perturbation, we will prove that the integral with the already perturbed eigenfunction is also positive for any x0, y0 belonging to the smallest part. But as we remember, if this integral is positive, then this is the contradiction with the fact that x0, y0 is a point of maximum. Therefore, we will, in this way, we will prove that any point from omega 1 cannot be the point of maximum, the point of extremum. Therefore, the point, since we know that for the convex sets, the point of maximum belongs to the set, therefore it follows that the point where O lambda 1 omega attains its maximum should belong only to the larger part of omega. Next, please. Yes, this is the sketch of the proof. Now, we will next pass to the next topic, and we are going to compare the ground state eigenvalue already with different omega and with the fixed x0. So first one, we will prove the theorem that For any x0, y0 and any omega, the ground state eigenvalue corresponding to this x0, y0 is no larger than the ground state eigenvalue of the Laplace operator. The right-hand side of this equation is the Laplace lambda 1 d omega is the Laplace operator with the Dirichlet conditions defined on omega. Also, we prove that in case if omega does not have the, it's written full rotational symmetry, which means that it is not disk or circular annulus with center such that x0, y0 becomes its center. Then, if we have no such situation, then this inequality is sharper. So this means that only less inequality for every positive omega. So if the domain has not rotational symmetric, then for any positive omega, the ground state eigenvalue is less than the ground state eigenvalue of the Laplace operator. Next, please. Now let's look on the situation when we have the rotational symmetry. For example, omega is a disk with center at the origin and radius r. And let omega be a small enough number, then we are going to prove that the ground state eigenvalue becomes equal to lambda 1 omega. So for the rotational symmetric sets and for small enough omega, this inequality, which we already discussed, becomes equation. Next, please. How to prove it again, the sketch. If we have the disk, then you can directly calculate the eigenvalues of our operators. But of course, in the terms of the special functions. Here, lambda 1 k omega are the eigenvalues. M are integer number and k are natural number. Then we have jmk, where jmk is the kth zero, positive zero of the Bessel function of the first kind, jm. R is the radius, and then omega, we have omega is our angular velocity, and m is an integer number. So in this situation, we directly calculate the eigenvalues. And then the first eigenvalue is, of course, the minimum of this set. Next, please. We prove the lemma that there exists a positive number, omega 0, such that if omega is less than omega 0, then the ground state eigenvalue larger or equal than j01 square over r square, where j01 is the Bessel. Can you go to the before slide? Yeah, you can see here what is the jmk. Already written jmk, what is that? So next slide, please. So we'll prove that jm1 larger or equal than j01 square over r square. Next, please. After that, we prove that we know that this right-hand side coincides with the ground state eigenvalue of the Laplace operator with Dirichlet boundary conditions on disk with the center of the origin. For the Dirichlet Laplacian, it doesn't matter where it's center. So this equal to the ground state eigenvalue of the Laplace operator on the disk with Dirichlet boundary conditions. And the next equation is the theorem which we already proved, that the ground state eigenvalue of operators, our operators, is no larger than the ground state eigenvalue of the Laplace operators. Next, please. And using this theorem and this lemma plus remark, we prove that we have that for small enough values of omega, the ground state eigenvalue of the operators, which we discuss, coincides with the ground state eigenvalue of the Laplace operators. So summarizing, we prove that the ground state eigenvalue of our operators is no larger than the ground state eigenvalue of the Laplace operators, but in some senses, if we have the rotational symmetric domain, it can, in some values of omega, they can coincide. Next, please. And now, in the last part of the talk, we can compare the ground state eigenvalue with the ground state eigenvalue of the same operator defined on the disk with the same area. And now it's written just that we add the index in our notations to fix the domain, to show the domain. So we have here, for example, lambda 1, omega already, small omega, only to mention that we speak about the domain omega. Next, please. Here we will speak again with convex regions, but it's not written here, but also what we will say later, it's also true for star-shaped regions. But here is written convex region. So for any convex region and any fixed x0, y0 belonging to this region, we will use this parametrization x0 plus r cosine phi and y0 plus r cosine phi in polar coordinates, where phi belongs to 0 to 2 pi and r belongs to 0 to r phi, where r phi is the domain parametrization and r is 2 pi periodic function. So we will use this representation of the domain. Next, please. So this is the theorem that if we have the domain omega and we have this its volume, then we will consider the disk B with the center at the origin and radius r0, which has the same volume as omega. Then if we look at our operator defined on omega, then the ground state eigenvalue can be estimated via the ground state eigenvalue of the same operator defined on this B plus something. And this something is given in the geometric properties of the domain, because here you have R function, which is the boundary function, boundary parametrization. And then you have here supremum, and then J is the Bessel function 0, some numbers. So we have this is the formula in terms of the geometric properties of the domain omega. And also there is written some asymptotics that for large enough values, this part goes to minus infinity, where omega goes to infinity. So also in this situation, one can, the open problem is to say about the Faber-Grad inequality, to show that the minimizer of such, minimizer of the ground state eigenvalue of our operator is the disk, as you can say about the Laplace operator. So this is the open question. So open question is to prove the upper inequalities, some upper inequalities somehow. Next, please. And also we will give here some sketch of the proof. So this is the representation, original representation of our operator. Next, please. And without loss of generality, suppose that x0, y0 is the origin. Then we pass to the polar coordinates. We get the Laplace operator defined on the polar coordinates and the perturbation of the Laplace operator, I omega multiply x minus x0, the partial derivatives, and y minus y0 multiplied by partial derivative. You can check that corresponds to the derivative with respect to phi. And then we can write down the quadratic form, which is written here. So first part of the integral corresponds to the Laplace operator, and the second is this angular operator. Next, please. Then we are going to pass to the new coordinates, to pass t multiply r phi, where t belongs to 0, 1, to do this change of the variables. And this change of variables, for example, this method appears in the work of Antunes, Freitas, Krejcik, bound state, bounds and extremal domains for Robin eigenvalues with negative boundary parameter. And this is the suitable change of coordinates. Next, please. Then, using these coordinates, we can rewrite the quadratic form into this way. It's more easier to work on this integral because next, please, and next, please. Because we know from minimax principle that the ground state eigenvalue, the last line, is less or equal than infimum. In fact, it's equal to the infimum, where u has a normalized eigenfunction, and the quadratic form at u. Quadratic form we already calculate. Now, choosing any function at the quadratic form, we will get the less. We will get that it is upper bound for the ground state eigenvalue. Now choosing the V instead of V, the ground state eigenfunction of our operator defined on disk, since we already discussed that our operator defined on disk has one can directly calculate these eigenvalues and also eigenfunctions. So we have the information for the eigenfunctions. Therefore, we can put it into the formula which is which is the first formula in this slide, and doing some estimates, we get the desired formula. And next, please. So this is what I wanted to say. And now the open problem becomes to prove some Faber-Grand inequality in this to complete this theory. And this is where these results are published. So thank you for your attention.